Welcome to Let's Get to the Marks. This is my part three or video three of the energetics pack for a walkthrough for the energetics, whatever. I don't even know what I'm talking about at this point. Yeah, this is video number three on energetics, physicsandmathstutor.com, going through that awesome website, checking out the AQA chemistry A-level pack on energetics. This is going to be the last part, so I'm going to do question 14 to 20. You can check out the other two parts. Seems to have been a popular video, so let's get into it. Question 14. A student planned and carried out an experiment to determine the enthalpy of reaction when magnesium metal displaces zinc from aqueous zinc sulfate. So we've got an equation here, magnesium plus zinc ions, obviously from the zinc sulfate solution, and they're displacing the magnesium, or the magnesium is displacing the zinc ion, sorry. So you're ending up with a magnesium sulfate and zinc metal being displaced. The student used this method. A measuring cylinder was used to transfer 50 centimeter cubed of a 1 mole DM aqueous solution of zinc sulfate. Now, the moment you see that, get into the habit, peeps. Annotate your work. So volume. This looks like a concentration, and that immediately makes you think of this equation, N over C times V. And that's the zinc sulfate. A thermometer was placed in the beaker. Okay, so we got temperature going on. 2.08 grams of magnesium. Boy, I got mass. Okay, once I start thinking we got moles there, and that means that we're probably going to be bussing out this calculation with mass, MR times moles. So as I'm going through, I'm dissecting and labeling the data. So we got 2.08 grams of magnesium metal powder, which were added to the beaker. The mixture was stirred and the maximum temperature recorded R. So we got maximum temp. Right, so we're going to be looking for temperature change as well, aren't we? The student recorded, yeah, there we go, starting temp and a maximum temperature of 61.2. Okay, so we got the temperature change just over here. Show by calculation which reactant was in excess, first of all. Use the data to calculate the experimental value for the enthalpy of reaction in kilojoule per mole. Assume the specific heat capacity of the solution is 4.18 and the density of the solution is 1g per cm cubed. Okay, cool. Let's get into it. By the way, this is a 6 fat marker, so let's go. So first of all, they want us to see which of the reactants are in excess. So just in case you're wondering what the hell the reactants are, we've got magnesium and we've got zinc sulfate. And the zinc sulfate, we've got 50 centimeters and 1 mole. So we need to do 50 over 1,000 because we have to change volume into decimeters. So that's our volume. And we're going to times that by the conc, which is 1. And that's going to give us 0.05 whoa, moles, right? Yeah, that's going to give us 0.05 moles, and that's of the old zinc sulfateous. So there we go. We've got zinc sulfate, 0. Blah, 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 blah. What am I waffling about? And then here's the other reactant. That's our magnesium over there. We got 2.08 of that. So I'm going to use this to calculate that. So I'm going to do 2.08 G over 24. Don't forget the 0.3. What is this going to equal? 2.08 divided by 24.3 equals, on the old calc, bash 0.08559. I got to round that to 0.08. 0.0856 or 0.086. What can we give that? Let's give that 0.0. I could just leave it as it is, whatever. But we can see that this is in excess. Okay, so if I do that, 0.0856, we can see that's in excess, right? It's 0.0356 greater than that. So I now know the limiting reaction, the limiting reagent, sorry, talking about limiting reactions. The limiting reagent is the zinc sulfate. So we've now worked out what's limiting. Oh, asked us for what's in excess. There we go. Always highlight the question because I didn't bother. So if that's limiting, because we've got 0.05 of that, then it's the Mg that's in excess. So we're going to have some floating metal magnesium hanging around. Excess, and I'd say it's by 0.0356 moles in excess. You could work out the mass that's left over if you really wanted by timesing that by 24.3. Yeah, I don't need to do it. Okay, you've already hit the marks for that. So We've already got the marks for working out the magnesiums in excess. Now we probably got 2 marks for this. Now we're going to get 4 marks for the old. What are we working out now? We're working out the um, we want the enthalpy of the reaction. So, the kilojoules per mole to the -1. That's what we want for the reaction. So I'm going to use the other side of this to do this. Excuse me while I boss out the equation. Q equals mc delta T. So now what we need to do, we need to work out Q, don't we? So we've got the mass. What was the mass? Well, you might make the mistake of using 2.08. We use that for calculating the moles. Uh, that's not the total mass. We've got 50 centimeter cubed. So our mass, and it told us the density, there's a reason for that. The mass, 50 centimeter cubed times density of 1. So volume times density equals mass. We have a mass of 50. We have a specific heat capacity, which is C, of 4.18. And then we need to bus out the temperature change. So I'm going to times that by the difference between 61.2 minus 23.9. So if you put that in your calc, what was that? I've already forgotten. 61.2 minus 23.9. And that gives us a temperature change of 37.3. So let's smash this in the calculator and work out Q. And that is definitely going to get us a mark. So let's bash that in. Times 50 times 4.18. And that gives us 7,700. So we end up with 7,790, what is it? 5.7, I believe, joules. Let me just double bubble. Yeah, that's right. So that's joules. Now we've got Q, so that's fantastic. You probably got yourself 4 fat marks for working out Q here and for working out the limiting reactants. We want all 6 marks. So now we need to convert this into kilojoules and then into per mole. So to convert to kilojoules, I need to divide that by 1,000. So divide by 1,000, and that's going to get us into kJ, and it's 7.7957. 7.7957. That is kilojoules. I now need to put that in per mole. So I'm going to divide that by the number of moles. Which one do we use? Well, we have to use whatever is limiting. If they're both equal, we can use either one. But in this situation, we've got a limiting reactant. So the reaction is going to finish after this amount of moles are used. So I'm going to divide that by 0.05, and that is going to give me, divided by 0.05, 155.9. So that gives me 155.9 kJ per mole -1. Give myself a little tick for that, please, Bob. Thank you. And then this A level, let's bash it to 3 significant figures. So 156. Why are we doing that? Because that is greater than 5 or greater than 4. So we're pushing that up to 156. And that is kilojoule per mole -1. Oh my gosh, is that how you write mole, Tom? That's disgusting. Right, 156 kilojoule per mole -1. And that gets you all of that 6 marks. Okay, let's zing to the next part of the question. Another student used the same method but got a different value, right? They got -142 kilojoule per mole to the -1. A data book a value for the enthalpy of reaction is -310. So the actual kind of real data book value is -310. Suggests the most likely reason for the large difference between the student's experimental value and the data book. So I'm imagining the reason there's a large reason is because we didn't use a polystyrene cup or there wasn't a lid or something like that. I didn't really pay attention to the equipment, but if we bush back up here, what did they put it in? It was placed in a beaker. It doesn't sound like they used much insulation. So I would say heat loss. Um, oh my gosh, I'm in white because I was writing on the side of the page. So let's go heat loss. To the surroundings. So our answer was less. exothermic. Obviously, it didn't seem like as much heat was released. So our answer was less exothermic than it should have been. Okay, um, let's move on. Zinging down suggests how the student's method and analysis of the results could be improved in order to determine a more accurate value for the enthalpy of reaction. Justify your suggestions, as that's very nice. Do not refer to the precision of the measuring equipment. Okay. Do not change the amounts. Okay. If we change what they're saying is basically they don't want you. The kind of answer you could bust down here is that if you increase or yeah, what am I waffling about? If we decrease the concentrations and things like that, or we change the amounts and whatever it is, we get a larger heat change. So if we increase the concentration or increase the moles and we get a greater heat change, there will be, for a greater delta T, we're going to get a smaller percentage error. But they're saying don't use that. So ours is all going to be about the apparatus, not the precision of it, but about the apparatus. So what can we do, change to the apparatus to make sure that we get accurate results? Well, what we can do is this. So I would do insulate apparatus to reduce heat loss, e.g. we want to use a polystyrene cup, cotton wool in beaker, use a lid, you get the idea. Any of this kind of stuff is going to reduce the heat loss to the surroundings and mean that we get a more exothermic value closer to that minus 310. What else can we do? What we should do is, rather than just taking an initial temperature and then the final temperature, we should take several initial temp readings. I probably should give a number there because sometimes they get funky about the word several. So I'm going to say take 3 initial temp readings, plot on graph. Ba, ba, ba. Then after addition of, in this case, solid, it was magnesium if we're still referring to the earlier stem of the question. So then after addition of magnesium or solid, take readings every 30 seconds for 5 minutes. So if we do that, we're going to be taking 10 more readings. We're then going to say, plot a graph. Yeah, plot a graph of what we're doing. Plot a graph of temp, whoa, against time. So we're going to do a graph of temperature against time, and we are then going to extrapolate the lines, or draw a line of best fit. I'm going to, oh my gosh, I'm running out of room. Draw a line of best fit, extrapolate lines to find initial temp and final temp. So what we're going to do, we're going to extrapolate the lines to find the initial temp and the final temp, or the temperature at the point of addition, and therefore it's going to be a lot more accurate. That's going to look something like this, just in case you're wondering. It's going to look something like this. So if we had a temperature increase, we take those first 3, and by the way, don't be afraid to sketch on the, don't be afraid to sketch on your 6 marker. The examiner may award you points for a little bit of an old sketch. So here I've got temperature. Obviously, you need to be a bit more accurate than me and label things properly. There's temperature, there's time. So I'm taking readings. I don't know, these are every 30 seconds or whatever. So got some initial readings. Then what we're going to find is the temperature goes up and then whatever. And then what I'm going to do is I'm going to draw some extrapolation lines. And then at the point that they cross there, I can calculate my delta T. So I've got like my final temperature. I can take this as like my initial temperature, and then I can calculate my delta T. So that's how we're going to do this more accurately. Okay, guys, let's zing on. Question 15. This question is about enthalpy changes. Write an equation including state symbols to show the reaction taking place when the standard enthalpy of combustion for ethanol is measured. So we just want to draw out ethanol. So enthalpy of combustion, they're just writing you to write an equation for the combustion of ethanol. So, oh, no, we don't want to write half O2. It's a bit dumb. When you completely combust in oxygen. So, ah, right. How many carbons? Two. So I'm going to make two carbon dioxides. How many hydrogens? There's six over there. So I need a three there. That means I've got three. Two times two is, what's that? Oh my God, I've gone mad. Two times two is four. Plus three is seven. There are three oxygens over. Oh, that's fine. I just need a three there. Don't forget you got one there. So you've actually got seven oxygens over here. If I put the three there, oh, just killed that fruit fly. That's a bit mean. Okay, there we go. 2 marks. Beautiful. Right, part B. Whoops. State the name given to the enthalpy change represented by the following chemical equation. Explain why the enthalpy change would be difficult to determine directly. So we've got carbon solid plus half an oxygen molecule goes to carbon monoxide. The enthalpy change, you can see here, we're making 1 mole of a compound, right? There's just 1 mole. There's no numbers in front of it. From its elements under standard conditions, i.e. oxygen when it's gaseous and carbon when it's solid. It doesn't matter how many moles of these you have to use, but for the enthalpy of formation, you got to form just 1 mole of a compound. So it's going to be enthalpy of formation. Enthalpy of formation. Now, it does say explain why it's difficult to determine directly. Obviously, it's not often you're going to have exactly half a mole of oxygen hanging around. What's going to happen if you have more oxygen? If you have any more oxygen, this carbon monoxide is going to readily form carbon dioxide. So what we want to say is um, carbon monoxide would react with oxygen to form CO2. So basically, it's going to be very hard to just keep it at carbon monoxide unless you can limit the amount of oxygen. If you're doing it in a closed system where you can limit the amount of oxygen massively, even then, some of that oxygen is going to react with some of the carbon monoxide that's forming and make make CO2. All right, let's move on. Let's move on. Let's move on. Part C. I need to make this a bit bigger. I can barely see with my rummy vision. Standard enthalpies of combustion for carbon and carbon monoxide are -393 kilojoule per mole, -283 kilojoule per mole, respectively. Use these data to calculate the enthalpy change for the reaction in part B. So what I need to do is write out the reaction from part B, which was, what was it? C plus half O2. I'm not going to use the state symbols, guys, because it's just long for me to draw them out. Okay, so they want us to work out the enthalpy change here, and they've given us the enthalpies of combustion. So if you burn carbon, you're going to make carbon dioxide, right? And we're going to make, if we burn carbon monoxide, we're going to make carbon dioxide. So let's have a little look. That's -393. This is -283. Notice my arrows are going down from this plus oxygen into carbon dioxide. We don't need one for oxygen because oxygen plus oxygen, whatever. So all I have to do now is draw my kind of magic arrow going around this way. And they won't no, they won't enthalpies of formation. This is all right. We keep this the same. So it's going to be -393 plus 283. And what does that equal? That is going to be like -110 kilojoule per mole -1. Sorry, that's in pink. That's a bit ugly to see. But yeah, so I like to draw the arrow going around clockwise. The only other way this can work is if we were given enthalpies of formation instead of doing combustion, then we would have had arrows going up from the elements. And then that means that you reverse the left-hand side and keep the right-hand side the same symbol. But on this case, when it's combustion data, you keep the left-hand side the same and you reverse the right-hand side symbol, bang them together, and you get your answer -110. Okay, that's 2 fat marks. Bish bish. Let's move on. All right, I'm on part D. Use the following data to calculate a value for the XEF bond enthalpy in XEF4. So, zibbidibidim, bibbidibidim, bibbidibidim, bibbidibidibidim. Right. Well, this is like those ones you did at GCSE. They've just given it to you in a more disgusting format, right? So they're giving you this in a disgusting format. We know that um, if you remember from GCSE, let me change that up, right? Okay. You remember that reactants, you got the energy going in, energy being absorbed, minus the energy being released um, from bond making is equal to the overall energy change. And that in this case is minus 252. They've told us the enthalpy change for the reaction is minus 252. So this is the energy change. So I just need to work out what the reactants are and what the products are and what the energy change is. And so let's do it. Let's do it. Do it. Do it. So we have, oh, they've given us the, basically what's happening here is we're atomizing F, right? And we're turning it into 2F. So we've broken the bond. So that is the bond energy. So my reactants over here on this side of the equation is going to be 2 times 158. It's plus 158. You get that. And what does that equal? That equals 316. Yeah, I think that equals 316. Then I'm going to put a minus sign. No, I'm not going to put, yeah, I'm going to put a minus sign. So plus 316 minus, we don't have any information for this because this is what we're working out. So minus the XEF bond from that, and there's four of them. So minus 4 XEF, oh my God, that's looking ugly, equals minus 252. So what do I need to do here? I just need to, that's plus 316. I can just take 316 from each side. Yeah, of course I can. Super. Okay, so let's minus 316 from each side. We just want to simplify. See if you can have a go at this. The minus 316 from each side is going to leave me with, let me write in black. This writing in pink is doing my nutting. It's going to leave me with nothing on the left other than minus 4 times the xenon and the fluorine bond like that. And that is going to equal, what is minus 252 minus 316? So minus 252 minus 316 equals minus 568. Hopefully I got this right. Now what I want to do is divide both sides by minus 4, right? To get rid of the minus 4, I need to divide both sides by the minus 4. And that is going to give me XEF is going to be equal to, what's that divided by minus 4? Equals 142. Boom! And there's no negative sign there because you're doing a minus divided by a minus. So 142 kg mole to the minus 1. There we go. Hope that helped. That is 3 fat marks. That's quite difficult because the way they set this out, but essentially they're asking you a value for the bond enthalpy. So just work it like you do at GCSE, where you do reactants minus product equals the energy change, and just try and, it's a little bit more difficult to work out what to put into that reactants minus products equals the energy change equation. And that is it really. Okay. Oh, I've got a part E. Suggest a reason why the value calculated in part D differs from the mean bond enthalpy. Oh, we know that, don't we? Mean bond enthalpies are always going to be different because they're not made from just the XEF. They're made from other compounds that contain that bond. So mean bond enthalpies are calculated from a range of compounds that contain the XE-F bond. Honestly, I really don't know how many compounds actually contain that bond. I thought that was a pretty rare bond, but yeah, what are we going to do? That's a standardized answer. I haven't looked that up myself. Okay. Question 16. Let's get on with it. A student carried out a reaction between magnesium ribbon and aqueous trichloroethanoic acid in order to determine the enthalpy change. The equation for the reaction is magnesium solid plus 2 hydrogen ion aqueous, basically acidic. Yeah, that's the trichloroethanoic acid. Goes to magnesium 2 plus ions. That's the yeah, that's going to be the magnesium salt that's formed plus hydrogen gas. Okay, it's been given off. The student measured the initial temperature of the trichloroethanoic acid, and again every minute for 3 minutes. Good. Before adding the magnesium ribbon at the fourth minute, that's the point of addition. The student continued to measure the temperature every minute for a further 10 minutes. See the graph. The graph for these measurements below is shown below. God, I can't speak. Okay, cool. I can see your graph. You've got temperature and time. You can see here, these are the whatchamacallit flicks. These are the three measurements, and then they added there. Okay. The student used 240 milligram of magnesium and 10 centimeter cubed of aqueous triethanoic acid in excess. Use these data and information determined from the graph above to calculate the enthalpy change in kilojoule per mole for this reaction. Show your working. Give your answer to an appropriate precision, i.e. 3 sig, right? Specific or 2 decimal places maybe, but 3 sig we go with at A level. The specific heat capacity of water is 4.18. Okay, 7 fat marks. All right. Let's get into this one. This should be easy. Once you get used to these, you will be fully prepared for one that a lot of students get wrong, so you can get ahead of the crowd with this. All right. We can tell straight away. Let's do our little sensible thing we like to do. What's this? We got mass. What's this? We got volume. Um, what else we got? What else we got? What else we got? What else we got? We have specific heat capacity. Right. So straight away, I'm gonna think we are definitely 100% off the bat going to need Q equals MC delta T. So straight off, I'm going to go, it tells us we got to use the graph. So I'm going to go up and use the graph to find delta T. And then we're going to work our way round to Q using the mass and the specific heat capacity, or is that the mass, the volume? Because we also need to take into account that density is equal to mass over volume. And generally, the density of water is 1 gram, right? And they're doing the specific heat capacity to water. So we're going to assume this 10 is 10 grams. So we're probably going to do that. All right, enough of my waffle. Let's get up. All right, here we go. What you got to do in these situations, peeps, it can be a bit confusing, but we need to draw a line here. We got our point of addition. So this is the initial temperature. What's that? Each one of these is worth what we got 10 squares. Yeah. Uh, we got 5 degrees over 10 squares. So each square is worth 0.5. So what do we reckon that is? That's 22.5, halfway between 25 and another one. I'm going to say that's 23 degrees. That's my take on it. Don't know what you think. Remember, they will judge your answer on yeah, what you do. So then they've taken a whole bunch of other readings every minute, and we've got a steady pattern. So I'm going to follow that pattern and draw a line of best fit like this. Yeah, bit crusty, isn't it? Follow that back to the point of extrapolation. So what do we reckon about there? About 40, it looks like. Draw that down. So here's me extrapolation lines, and we are intersecting this line and this line are kind of intersecting about there, aren't they? That's where they're intersecting. So at 40 degrees. So I would say the delta T, the temperature change, is 40 minus 23 equals 17 degrees. That's what I'm going with, peeps. All right, I'm going to delete this because I want to go back down and do the rest of the calculation. Keep that in your brain. 17-degree temperature change. Now have a go at this using Q equals MC delta T. So here we go. Going to go through the answers. Q equals MC delta T. So we've got the delta T. We need Q. So let's do the mass. The mass here is going to be 10. It's not this, by the way. You might say, what it? But it's not that. Why is it? Because we're always using the solution in these Q equals MC squared, and each centimeter cubed is generally worth 1 gram, unless they tell you otherwise. Sometimes they get funny and they go like it's 1.01 grams, the density of whatever solution. Anywho, enough of my waffle. We're going to do mass, which is 10 times 4.18. I'm going to times that by 17, but you times it by what you worked out on your graph, but you'll know you're far off if you've got something completely different. But you may be a bit more accurate than me. So this equals, I believe, 710 0.6, and that is going to be joules. Okay, that is Q. Now, bearing in mind, we want kilojoules per mole. So I need to convert that first of all to kilojoules. So I'm going to divide by 1,000. So that is going to give me kilojoules. And the kilojoules are 0.7016. So equals 0. I forgot the point. 7. Did I say oh? No, it's 7106. You bleh, head. 0.7016, that's kJ. Now, what does this mole to the minus one mean? This mole to the minus one means divided by the moles. So I need to divide that by the moles. We're going to have to work out the moles. We're going to need to do the old mass over MR times moles. What we got? We got 240 milligrams. That's a magnesium. So 240 divided by 1,000. Why? We need to get rid of the little m, people. So we got 0.240 grams. We're then going to divide that by 24.3. Oh my days, that looks like 2 plus 24.3. What the hell does that equal? So let's do 0.240 divided by 24.3. Smash that in the calc. Press the old SD button, and I'm going to get 9.8765. I'm going to round that to 9.88. So I got 9.8765 times 10 to the minus 3. Going to round that to 9.88, make it look a bit neater, times 10 to the minus 3. And then that is my moles. So I'm going to put that under 0.7106. So let's go 0.7106 divided by answer equals bish bash bosh. I got 71.948. Okay, so my final answer is 71.948. Now they said do it to appropriate precision. I'm going to go 3 sig fig, so I'm going to use it as 71.9. Hope that's good enough for the old mark scheme. So my final answer is actually going to be to 3SF. I'm going to do 71.9, and that is kilojoule mole minus 1. Hope that helps. It's a fast set of marks, wasn't it? But I suppose it included the graph work. All right, guys. Let's zing down. Let's get this back done. Question 17, got some multiple choice coming up. So the table shows the standard enthalpy of formation for some of the substances in the reaction. We've got ethane plus 6 fluorine molecules goes to whatever the hell that is. I'm not even going to attempt to say it. Hexafluoroethane, oh, whatever. Plus 6 hydrogen fluoride. And the enthalpy of this reaction is minus 2898. What is the standard enthalpy of formation for HF? So we want the standard enthalpy of formation for HF. What have we been given? We've been given some formation data for this and that. Okay. Okay. Right. What I'm going to do, how I'm going to do this, guys, I need to write this out because I have to do my crappy Hess's law cycle. I know you say, why do you have to do it like that? A lot of really good maths people do not need to write these out, but I am a bog standard maths brain, so I have to write these out. Okay, that's just me. So now this root is equal to minus 2898. Okay, that root. We've been given enthalpy of formation. So if I'm to form C2H6 from its elements, it's minus 84. What's its elements? Yeah, whatever. If I'm to form C2F6 from its elements, it's minus 1344. I've got no coefficients. Thank you, Lord. I don't have to do any multiplication. But what I am going to do is take an arrow, cheese Louise, draw it going this way, coming round, the arrow clashes. Where I get a clash, I reverse the sign. So that's going to become plus 84 for me. And if I write this out as an equation, remember, regardless of the root taken, it all equals the same. So it's going to be plus 84 minus 1344. Why do we keep that sign the same? Because my red arrow that I always do going anti-clockwise is going in the same direction. So I keep them the same, is equal to minus 2898. Oh, I haven't even written the what is the bond? The HF, 6HF. Sorry about that. Let's zing that into there as well. Gosh, missed that out. Silly Billy. Plus 6HF, because look, there should have been an HF thing there with our missing number, and I would have had to do 6 times this one here. HF. So that's why it's also on that side. So minus 344 plus 6HF is equal to minus 2898. I'm running out of room. Right, first things first, let's take away 84 from each side and then plus 1344 to each side to get rid of the numbers and then divide by 6 to find out what HF is. So I'm going to go minus 2898 minus 84 gives me that. Then I want a plus 1344 equals minus and then right. So let's go through that. I've just waffled my way, right? So first of all, I'm going to take away 84 from each side. And if I do that, I get minus 2898, take away 84. I want to do that. And I'm going to write this out again. I know it's getting cramped down here. It's getting a bit squishy squashy. Um, and I shouldn't be using red. What a terrible color. And now that equals minus 2982. I'm going to switch up colors. Now what I want to do is plus 1344 to each side to get rid of that 1344. So I'm going to end up with 6HF is equal to minus 298 plus 1344. And that gives me minus 1638. Now 6HF is equal to that. Divide both sides by 6. I'm going up the top. We're running out of room. And this tells me that HF is equal to minus, oh my days, 1638 over 6. Let's divide that by 6. We got minus 273. That was a lot of work for 1 mark. What? Okay. Question 18. What is the temperature rise in Kelvin when 504 joules of heat energy are absorbed by 0.110 kilograms of solid iron? Specific heat capacity 0.448. Right. This is nice and easy. Hopefully, he says. Easy peasy, lemon squeezy. We're just going to do that. They're asking us for what's the temperature rise? Great. So we need to rearrange Q over MC, divide both sides by mass and specific heat capacity to leave the temperature rise. They did say what is the temperature rise in Kelvin? Yeah, same as saying what is the temperature rise in degrees. That's just to throw you off. 1 degree is equal to 1 Kelvin. So Q is 504. Thanks for that, Bob. We now have that. The mass is going to be 0.110 times 1,000. Why? Because it's in kg and we're chemists. We don't like to use kg. So we are going to have 110 grams and we need to times that by 0.448. And what are you giving us? You're giving us 504 divided by 110 times 0.448, bosh, 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 equals 10.227. 10.227. And we can see it's going to have to be B, right? Because times 10, you're going to get 10.2 something or other. Yeah, that's lovely. Okay, hopefully you can see that there is the same as, or roughly the same as that there, roughly. Let's move on. There's only 20 questions, so we're getting there, we're getting there, we're getting there. Calculate the enthalpy change in kilojoule for this dissociation of calculate the enthalpy change in kilojoule for this dissociation of mole of propane 1. Oh gosh, I feel like I can't read either that or I'm a total idiot. Okay, so mean bond dissociation enthalpy. Calculate the enthalpy change in kilojoule for this dissociation. Oh yeah, that's easy. I've just got to add up all the bonds broken. So just add all the bonds broken up. There's nothing to do over this side. So what have we got? They've tried to be cheeky. You could draw the displayed formula out if you like, but should I draw the displayed out? It's just going to long out the video. So there are, oh, go on then. I'll do it. I'll do it. I'll do it. I'll do it. I mean, you can work it out without drawing it out, but it's probably best to show it all drawn out. I'm not going to bother drawing the hydrogens. So each one of these is a CH bond. So I've got 1, 2, 3, 4, 5, 6, 7. So I want to do 7 times 412. Bash that in the calc. 2, 8, 8, 4. And then I've got 2 times CC. So 2 times 3, 4, 8. So 2 times 3, 4, 8. That gives me 696. I'll probably make a mistake here. I'm always prone to mistakes. Oh, we've got a CO bond. Hello, Mr. CO. So we have 360 and we have an OH bond 463. What is that all when you add it up? Let's have a little go. 2884 plus 360 plus 463 equals, I feel like I'm missing something out. What am I missing out? Did I do the CO? Did I do the two cc's? Yeah, I missed out the six plus 696. Okay, because I'm an idiot. Right, that equals 4403. Beautiful. Oh my days. Right, so we've got two here. We've got to think, what are we doing? We're doing bond breaking, and bond breaking is endothermic, right? Bond making is exothermic. You know that from GCSE peeps. So C is the correct answer this time. They tried to catch us there. Brutal. Okay, lovely jubbly. Right, last question. Oh my gosh, how did it flick back there? I only tapped the keyboard. I've got some of them dodgy keyboards. Some budget HP thing. Right, the figure below shows apparatus used in an experiment to determine the enthalpy of combustion of leaf alcohol. So we've got some alcohol from a leaf, whatever that means. 50 grams of water. Okay, it's going to be the old Q equals MC, right? The alcohol is placed in a spirit burner and weighed. The burner is lit. The alcohol burned for a few minutes. The flame is extinguished. The burner is reweighed. Gordon Bennett. The temperature of the water is recorded before and after heating. The following table shows the results obtained. Initial mass of the spirit burner is 56.38. Final mass is 55.84. Let's just go ahead and work that out. We know these guys are going to tell us we need that. So let's work it out right now. Yeah, let's work it right. Oh, my days. Where's the white? There it is. Let's go 56.38. Take that away from 55.84. What am I on about? Okay. 56.38, take away 55.84. We can find that we have a mass of fuel used. We're probably going to need this to calculate moles. You should know the coup by now. One, GH. Oh gosh, it's all falling apart. It's the end of the vid. That's why it's all going wrong. Um, I'm burning out. Too early to burn out. Okay, so you got it. We've worked out the mass of fuel. That's mass of fuel, in case you're wondering. You might say, we haven't even read the question yet, but you want to get ahead of the game. Initial temp, final temp. Let's work that out, guys. We know that's delta T, so let's work it out. Change in temp. We know this is going to be Q equals MC delta T. We can tell already 40.8 minus 20.7, and that is equaling 20.1, if I'm not mistaken. I don't think I am. All right, let's go down and read the equation. Right, the equation, the question. Write an equation for the complete combustion of leaf alcohol. Oh, I'll probably make a mistake here because I probably can't add it up. How many C's have we got? One, two, three, four, five, six. Is that six? I'm going blind. One, two, three, four, five, six. I swear that's six. See how I get this wrong. You're the most depressed. How many hydrogens? One, two, three, four, five, six, seven, eight, nine, 10, 11, 12. Okay, I could do that, but then it doesn't look like alcohol, so I could do this as well. Both are correct. Don't worry yourself. Complete combustion, so we want O2, so we just want to go CO2, so we just want to go H2O, so we just want to go C6. I need 6 carbon dioxides. I've got 12 hydrogens there, so I need 6 waters. And then I'm going to need 6 times 2, and I need 6 times O. 12, 18, 9. Oh, no, not 9. They nearly caught me out. Sneaky, sneaky, sneaky. So altogether, I've got 12 oxygens there and I've got 6 there. That makes 18 oxy, right? But over here, we've already got a sneaky one there. So I only need 17 oxy. So I want to do 8.5 oxygens here. Yeah, because 8.5 times O2 is 17, and we've got the extra little bad boy over there. So those cheeky little kids trying to catch us out. Outrageous. All right, let's go down and do the final part of the question. I'm going to leave that bit on the right-hand side that I got from the table, so I ain't got to keep flicking up and down. Oh my good gosh, guys, massive, massive, massive help if you help me by hitting the like button because it really helps me out. All right, nice one. Use the results from the table above to calculate enthalpy of combustion detail. Give them boom. Okay, so I don't know if you remember, but it told us there were 50 grams being heated up of water. So we know that we need Q equals MC delta T. We know the temperature change is 20.1. I'm going to use 4.18 because it tells us that's the Q there. And we're going to use 50 because if you remember inside the spirit burner, you have to trust me on this, there was 50 centimeters or 50 grams of stuff. So it's 50 times 4.18 times 20.1. So 50 times 4.18 times 20.1. And that gives us a total of 4,200.9. I hope this is right. I haven't put a mistake in there. I probably have. Right. Did I do that right? 4.18? Yeah, I did. Okay. Next thing you know, the coup, we're going to divide by 1,000. We're going to get that into kilojoules. Whoops. 4.2009. And that's kJ. Now I need to divide by moles because we want our answer in kilojoule mole minus one, don't we, folks? That's what we do enthalpy changes in. So let's work out the moles. And the moles, oh my gosh, are 0.54 grams over the mass of the fuel. Oh my days. What was the mass of the fuel? What was the formula? We wrote it up there in that bloody equation. I don't want to move my screen. I think it was C6H12O. It was C6H12O. So 6 times 12, God, that's long, is 72, right? Plus 12. That's 84 plus 16. Nice. It's 100, the MR. So it's 100. That is some neat handwriting. And that equals 0.54 divided by 100 equals how many moles, please, Bob? 5.4 times 10 to the minus 3. So 5.4 times 10 to the minus 3. That is my moles of fuel that have been burnt. So let's go ahead and divide those kilojoules by that and find out what the enthalpy of combustion is. So it's going to be 4.2009 divided by 5, whoops, 5.4 times 10 to the minus 3 equals, that equals 777.9 kJ per mole minus 1. We can wrap that as 778. Boom. And there's 4 fat marks. 1, 2, 3, 4. Right, let's zing down. State how your answer to part B is likely to differ from the value quoted in the reference sources. Give one reason for your answer. So how is it likely to differ? Well, we're likely to have heat loss, or we can say incomplete combustion. Okay. Or we can say evaporation. Remember, it's an alcohol. They've told us that. So it's highly volatile. So you're going to get evaporation of fuel, which means you don't get to burn all the grams of fuel, which means you don't get such a big temperature change, which means answer is less exothermic. Now you've got to be really careful here. They're really picky on this. So I would say check this one out, right? Answer is less exothermic. If you say the answer is smaller, that might not get you the code because they might say, do you mean, or the answer is lower. They might say, oh, do you mean it's like minus 90 instead of minus 77 or minus 900 instead of minus 778? What are you saying by it's lower? Of course, we mean less exothermic. We mean it's going to be like minus 600 instead of minus 778. But that's why less exothermic is a better answer for these calorimetry ones. All right. Enough of my whiffle. I think this is the last part to the pack. Oh gosh, we're done. A 50-gram sample of water was used in this experiment. Explain how you could measure out this mass of water without using a balance. Right. We know 1 gram of water has a volume of 1 centimeter cubed. What does that tell you? The density is 1 gram per cm to the minus 3. So we could use a measuring cylinder. So we don't really need a balance because we know when we're heating water, that water, 1 gram is equivalent to 1 centimeter cubed. So we could bash out a measuring cylinder for it. All right, guys, I am absolutely mashed up and tired. Sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. It helps me out massively. Exams are coming. Let's go.
You're still here? It's over.